Good evening, all of you. My name is Anil Yadav. This is tutorial 5 on fundamentals of micro and nano fabrication. Most of the lectures are taken from Professor Sushovana's this uh, course. So today we will start with the another additive processing that previously we have seen on chemical vapor deposition. Today we will have a look on atomic layer deposition. This is another chemical additive processing. So let's get started. Okay. In atomic layer deposition, what happens is this is the basic. So if there in atomic layer deposition, what happens is we grow the material over the substrate layer by layer. A layer by layer growth means we grow this material atomically with atomically thin layers. First, one with the layer by layer growth is some kind of the atomic layer. This what to say? Atom by atom growth is happening over there. The growth is slow, but the film quality is very good in this case. Conformality, let's talk about the conformality that we have seen previously in definitions. So if there are very deep trenches in the silicon wafer, if you want to grow, you want to deposit a material, that should follow the same trench, that same morphology. In that case, the atomic layer deposition is the best. So it will get deposited over with the trenches with very high aspect ratio. In this case, the aspect ratio is let us say 1 by 1000. In this case, 1 by 1000 is like, let us say this is 1 micrometer. The width of this trench is 1 micrometer, and the trench height is 1000 micrometer. Okay, 1000 micrometer. In that case as well, that you can see this is the white layer deposited, a very thin white layer deposited over this, which is zinc oxide over our silicon wafer. There are trenches in the silicon wafer and it is completely following the same. And also that you can notice there are some roughness over this over the zinc oxide. The roughness, it is exactly following the same same morphology whatever was in the trench, because the trench itself was some rough. So that is why there is roughness over this or in the white layer. And the best part in this one is a very low temperature depositions can be possible, which is in between 150 to 300 degrees Celsius. So so it will consume lesser power and kind of these things. And a very wide variety of materials can be deposited through atomic layer depositions, like some oxides, metals, nitrides. In oxides, SiO2, Al2O3, TiO2, hafnium oxide, zinc oxide. So in this one, what you need is two precursors. One precursor which is containing silicon. If you are depositing silicon dioxide, one precursor is silicon. Another one is if you are depositing Al2O3. In Al2O3, what you need is there should be a aluminum containing precursor, and another one is oxidant that can oxidize that precursor over the substrate. Okay, that oxidant can be ozone, oxygen, and H2O. Any oxidizing agent which contains oxygen can be used for this. Not any, but that should not contaminate the layer as well. Okay, metals can be deposited, nitrides can be deposited. In nitrides, you for nitridation, like titanium nitride, one precursor should be containing titanium and another should be nitrogen. So here you what you cannot use is the nitrogen, N2. N2 and nitrogen are connected with triple bonds. Okay, a very high energy is required to break the bond that and to convert it N, and which is highly unstable as well. So in that case, what you can do is you can use ammonia, NH3, and or any other containing which have nitrogen which can provide nitrogen at lower temperatures. Okay, so one thing is the roughness, RMS roughness of this is less than 1 nanometer, because the it is layer by layer growth is happening, and very highly conformal growth you can get in this one. And that it will this ALD deposition will follow the same whatever there is in the on the substrate. Okay, so one ALD cycle typically this is the kind of mechanism how the ALD what is the for a typical ALD cycle, what is the typical ALD cycle. So for a deposition needs two components, A and B. A and B is like A is if you are depositing Al2O3, Al2O3, so A should be aluminum containing, B should be some oxygen containing. Okay, so initially what is there, there is a adsorbed what we will do is there is a chamber, let us say this is the chamber, there are two lines in this one, so we control these lines with some MFC or some valves. So we will pass the precursor A. Okay, we will pass the precursor A, that will be that will chemi-adsorbed over the substrate. Okay, so in the chemi-adsorbed is required. Chemi-adsorption is there is a formation of chemical bond of the precursor A with the substrate. So this should adsorb chemically, not the physical adsorption is physically adsorbed. Okay, that we will see why the physical adsorption is physical adsorption will give you a non-uniform growth. Okay, because there are some steps. Oh, first let us see this. What steps do you require for the ALD? Okay, so initially what will happen is this is chemically adsorbed over the substrate, and one thing is self-limiting. This is self-limiting. Self-limiting in the sense is there is only a single layer of the atoms is adsorbed over the substrate chemically, because the chemistry of the substrate is such that only that precursor A can form a bond over that, but no two A plus A cannot form. Okay, A plus A this precursor A will not react with the precursor A itself. Okay, so what will happen is, so only a single layer of the molecules will be formed over the substrate, and in the next cycle what we will do is, in the next cycle we will pass the precursor B. Okay, we will initially we are getting at this position, that can be okay, then next we will pass the precursor B. B is kind of oxidant. Okay, this precursor B will specifically react at these sites, will specifically react with the previous molecules. Okay, one on the top. So these are the reacted precursor. If we will give some time to this one, sometime let's say in milliseconds only, because these are highly reactive kind of precursors. So like if you are, the B precursor is nothing but H2O. Okay, A precursor is TMA, trimethyl aluminium, which is containing aluminium. Trimethyl aluminium is chemi-adsorbed over the substrate, and the next one after this chemical adsorption, H2O will come, and that will specifically react with the chemi-adsorbed TMA. Okay, this TMA, and it will if we will give sufficient time to this one, that is the whole time or soak time, or you can say yeah, these kind of things you can use, these kind of terminologies. So the reaction is self-limiting. In this case, only a single molecule will be react these self-limiting, this substrate will be covered with the B molecules. Okay, there will be ending with the B molecules. Okay, so in this case what happens is there will be some extra precursor will be in the chamber. Okay, so A reacts with B and B reacts with A, kind of this is the thing, but A does not reacts with A, but and B also, B does not reacts with B. If B would have reacted with the B itself, so it would have formed something else. Okay, so A plus B is there in after the nitrogen. So what we will do is we will flush this chamber. Now at this point we will flush this chamber with the nitrogen. Whatever extra precursor is available in this chamber, which is in the air, which is in the environment of the chamber, that will be removed with the nitrogen. Okay, nitrogen is because this is an inert gas. Either you can use nitrogen or argon. Usually nitrogen is used because that is less expensive than the argon. Argon is more expensive. That is why. So in nitrogen you can do that thing. You can flush the chamber with nitrogen. Now again what you will do is, again you will pass the precursor A. This precursor A will specifically react with these sites again. Okay, and that is too is self-limiting because of A will not react with A, so there won't be any A on top of the A. Okay, so initially this is the first one layer. So one layer of the molecule, if you, this is aluminium oxide Al2O3 you have prepared in this one. A single layer, single atomic layer of Al2O3 you have deposited in this cycle. Okay, so whatever from where we started, we were ending with the chemi-adsorbed A over the top, that you can see the red squares. So finally we are ending with the red squares. Now we will flush the chamber and we will come back at the same point, at this point. Okay, so this is typical cycle of an ALD process. Now what are the materials and precursors that can be used for the for atomic layer deposition? Let me check if someone is there. So what sort of ALD precursors are required? So precursors for cations like aluminium or aluminum oxide, like aluminium. So metal organics are specifically, we can say metal organics because they are highly kind of reactive. So metal organic complexes are there, not complexes. Trimethyl aluminum is used generally for aluminum oxide deposition. So usually metal organic or metal chlorides are used for ALD precursors. A vast variety of the precursors are available. Okay, metal alkyls, alkoxides, metalamines, amines for nitrides. Okay, so not nitrides because amines in okay, NH3 also gets removed easily if there is metal amine in that precursor. So and for oxides it is used generally used H2O2 or O3 to oxidize the precursor, okay, on the substrate. And for with the plasma ion, N2O can be used and CO2 can be used. In plasma enhanced CVD, that ALD, that we will see a lower temperature is required, because to provide the energy we are in thermal ALD we are providing with the temperature, but in plasma ALD we can provide the energy with the plasma. Okay, so generally for nitrides NH3 is used, for sulfides H2S is used, for phosphides pH3 is used instead of H2O, O2 or O3 for oxides that we are using for the oxides. And for aluminium, like it is aluminium containing for aluminium, trimethyl aluminum is used. This is organometallic precursor, and this is again then another organometallic precursor which is diethyl zinc. And these kind of precursors are used. So some are very small in size, some are very large in size, but these precursors are kind of highly reactive. So precautions should be there, because these are kind of pyrophoric. If they come in contact with the water in the environment, in the outer environment, they will catch fire, and they are hazardous to environment as well. Okay. So let me show you the ALD using by deposition of Al2O3 using trimethyl aluminum. So in very first step, this is the substrate, like silicon substrate is there. In silicon there are always the OH bonds. The OH bonds are terminated as soon as you keep it in outside environment. There will be a termination of the OH bond, or if there that is not that much reactive, what you can do is you can keep it in the moisture for some time and then you can use that. So after these OH bonds are the reactive sites. This oxygen is the reactive sites for trimethyl aluminum. So what will happen is this aluminum will react, will attack over this one. This is kind of a Lewis acid base reaction. So there are there is a base, OH will act as the base. This will be a Lewis acid. So there are lone pair. There is lone pair of electrons and there is vacant orbitals in this aluminum. So there will be a kind of complex that will be formed after you pass the precursor, this aluminum trimethyl aluminum inside this one. So this CH3 will be after the reaction, this CH3 will be a byproduct of this reaction, and this aluminum is connected with the oxygen, so and after that you will purge the system so that you excess of the precursor you should get removed. After the purging you will pass the H2O. Okay, in this case as well, when H2O will react with the aluminum, this CH3 will get removed, and this H2O again that same Lewis acid base reaction will happen, and this is again is terminated with the OH bonds. Okay, from where we started with the OH termination, and again we got the OH termination. Okay, and now this typically represents the single cycle, one cycle of the one atomic layer of Al2O3 is deposited over this one. Okay, and And another thing is the best part of aluminum of this one is, okay, again I need to, I think there are no, no. So best part of the it forms very dense and conformal Al2O3, because when we pass this is a gas phase reaction, so it can go at very small, because the size of aluminum is of this precursor is very less. So if you need a conformal coating, this precursor can go inside the trench and can react to the specifically at the sites. Inside the trench it can go easily. But if you are doing something kind of deposition, like a physical deposition, that will go, the physical deposition that we will cover in the today only. So in that case, there is no the side walls are not covered in that case, but it chemically reacts at the side walls. That is why there is a conformal deposition in this. And layer by layer growth of in ALD. This is the typical ALD cycle. In first, you will give a TMA dosed. You can call it dose, hold time, or whatever. This is the TMA dose. TMA dose, the time that you give that soak time or hold time, you can say. So this is the time. Okay, this is the time. This is the hold time or soak time. Yeah, you give a TMA dose, then you purge to remove the excess TMA in the chamber. You will purge with nitrogen, and to oxidize it, you will pass the H2O or oxygen or ozone that will react with the TMA and will form Al2O3. And then again, to remove that excess of H2O, you will do that, purge it with the nitrogen. So this is the mass gain over the substrate in that one. Okay, that is nanogram per centimeter square, it is saying. So in this one, what happens, this is done with the crystal monitor. Okay, so what happens in this one, initially we will give a TMA dose. What is the mass gain of the on the crystal monitor is, initially it will increase, and it will get saturated. Okay, whatever, how much TMA you will give after this point, after the saturation point, will not affect the any mass gain, further mass gain, because TMA is not reacting with TMA itself, right? But TMA, whatever TMA has to react, that has already reacted on the surface, that is already formed a monolayer of TMA, and after that you will remove the excess precursor. Okay, excess precursor from the chamber. So at this point you will purge it with the nitrogen. During nitrogen purging, there is no loss of the of mass or from the substrate. It shows that this TMA is chemically adsorbed over the substrate, because if it would have reacted physically, physical adsorption gets removed when you purge the system. Okay, so that is why the chemical adsorption is required. And after that, what you do is you do give a dose of H2O that will react with the water. Okay, that this previous layer, this TMA will react with water, like Lewis acid base reaction, and at that point there will also come a saturation point. Okay, and at this point, if you give a further H2, that won't affect that much, because there may be any some kind of and after that you give this H2O has reacted chemically as well as physical adsorption is also there. So that physical adsorption, adsorbed H2O gets removed during the purge time, and that chemically adsorbed, chemically reacted H2O that has already formed the Al2O3. Okay, that has already formed Al2O3 will remain, because that cannot be removed. And further, this is the increase. And there is small part of this, there is a like dip in the mass gain. That mass, that can be because of there is a removal of CH3 as well. Okay, two molecules of CH3 gets removed when oxygen is added. So that is also, that will also be affecting, because the mass of CH3 is also removing after the chemical reaction. And the growth rate is like a thickness per cycle. Okay, GPC, the growth per cycle that we can see, say growth per cycle, that is the GPC. Okay, so this ALD process proceeds with a series of self-limiting growth steps. Okay, so in this one, a single cycle, how much growth is happening in a single cycle, that we will see. So we can do a multiple number of cycles, let's say 100 cycles we have done, and we will measure the thickness of this one, the total thickness of the layer, and that we will divide by 100, and we will see how much the thickness, what is the growth rate, okay, per cycle. So growth rate is linear with numbers and steps, and if you zoom in, this is the growth rate. Okay, this is number of this side the time which is the number of cycles that you can say, and this is the Al2O3 thickness. Okay, so the thickness is linearly increasing with the time. If we zoom in that one, that is a step kind of function. Okay, step kind of because with one step, this height is nothing but that is the Al2O3 thickness with single cycle. Okay, which is around 1.07 angstrom. Okay, typically, or can be 1.1 or sometime. So that is that depends on substrate as well, or the system. Okay, now why do you need, okay, so this self-limiting nature of chemisorption in, so this is a typical growth rate. Okay, growth rate, or you can say the mass gain as well. This is the typically sign. I think someone wants to join. No. Okay, in this one, this is the kind of mass gain, or the growth rate per cycle. So in this case, this is the dose time. Dose time is how much time you are giving, you are exposing the substrate with the precursor. So if let us say you are exposing the substrate with the precursor till this time only, but this is the under the substrate is not fully covered with the zinc oxide. Okay, the substrate is not the dose time is very less, to the doses that you have given is very less to cover the whole substrate. So you will increase the time, and there will be a time that comes, then it will get saturated. Okay, that will get saturated, and the from this point onwards, this is chemically, this is you are wasting your time. If you are giving a more dose time, you are wasting your time, as well as the material itself, material also. Okay, so dose time should be defined, that should be that much only, at till that time it gets saturated, otherwise you will be wasting your time and material. Okay, so and in another thing is, okay, so why it should be 100% coverage. Below this one it is less than 100%, after this one it is 100%. So so typical dose time should be above this one. Okay, above this one. And one another thing is, this is independent of the pressure. So how much pressure you will give the partial pressure of your precursor, that won't affect the the growth rate. Okay, that it should be enough. The partial pressure won't affect, but the material should be enough that it should cover the whole substrate. It should not be too less so that this time will be increased too much. Okay, it should not be less as well. It should not be high, because otherwise you will be wasting your material. Okay, so the best part is it is independent of the vapor pressure of the material of the precursor, so it won't affect, unlike CVD. So in CVD you it won't affect the growth rate. Okay, growth rate will be constant with the any kind of the partial pressure. And another thing is chemisorption. In unlike this is kind of physi-adsorption or adsorption, it is irreversible. So during the purge time it is not getting removed. Okay, this is not getting removed because it is chemically attached with the substrate. Okay, and this is the same thing, deposition per cycle or the mass gain per cycle is the, this is the time, this is the dosage time. Okay, so you should be in this regime, always in this regime. After this should be your soak time or your dosage time. Okay, this should be your dosage time for the precursor 1, that is maybe for for aluminum this is TMA, let us say TMA. Okay, for and this in this region, this is the okay, there are two things for if you want to optimize an ALD process. What how you can do that is you just need to define the soak time of precursor 1 and purge time of precursor 1, and also you need to do the same for the precursor 2, soak time for the precursor 2 and purge time for the precursor 2. So through this you can optimize the process. Only 4 parameters are there and that can be easily done. Okay, that can be easily done. So this is a typical graph of the soak time, and this one, the orange one, is the typical for the purge time. Okay, this is so your soak time should be greater than this one, your purge time should be greater than this one. Purge time is the okay, if your soak time is less than this one, so there won't be any full coverage of the TMA. Okay, on the substrate, so there will be some kind of islands or some kind of the growth will not be kind of uniform. There will be undergrown of the Al2O3, because TMA is not enough to cover the whole substrate. So, and if you have done the TMA dose should be more than this one this time, and further you need to remove the excess TMA. Okay, you need to remove the excess TMA from the chamber. So how can you remove that? By purging, by passing the nitrogen through the chamber. Okay, so that will also, that the time for that will be this is the TMA is coming down, the concentration of TMA, excess TMA in the chamber is down and down. So this will get saturated. Okay, that is the, at this point this is the chemically adsorbed TMA in the on the substrate. Okay, so we have removed the TMA, but that purge time should be more than this one. Okay, so more than this one, that should be at this point only. If you are increasing this time, you are just wasting your time and the resources. Okay, and okay, further is this is for the half cycle of the TMA, and this the same thing happens for the H2O as well. So if you are giving the H2O dose, the dose should be till this point. Okay, it should be above this point, but you should not go beyond too much, otherwise you are wasting the time. And below this, that is the too less of H2O to oxidize the TMA or the substrate. Okay, and also then again you need to do the purging of the H2O. H2O purge you have done with the nitrogen or argon. So if your purge time is less than this one, so what will happen is there is already H2O inside the chamber. Okay, so when you give the doses of TMA, that will react in the environment with the H2O, and it will rain down the kind of the particles over the substrate. So a kind of CVD like growth will happen. In CVD, what we will do is we do is we simultaneously pass the all the both the precursors inside the chamber. They specifically react with at the higher temperatures with the substrate and forms the material over that, deposits the material. But in this case, what we do is we do it layer by layer. The growth rate is very less as compared to CVD, because in that every time this material is available, that gaseous precursors are available in the chamber. So the reaction is too fast because of the availability of the precursor. So in this one we do give alternate cycles of the precursors. Okay, so in this regime, or in the regime, so there will be a non-uniformity over the wafer. So that is the thing we do not want. Okay, effect of insufficient doses, or if you are in this regime, so in this regime of the soak time, so what will happen is in this regime there is a suboptimal growth. And it, okay, let us say this is the chamber, and inside that there is a wafer. So this is the inlet of the precursor, and this is the outlet of the precursor. The availability of the precursor at this point is will be more than this point, because the precursor is consumed in this region already. Okay, the suboptimal regime, so the dosage time is very less. Because of that, the growth will happen specifically in this region, and in this region there will be very less growth. So for that you need to increase the dosage time or the soak time, or you need to increase the dosage. Okay, so in this regime there will be a full coverage of the wafer with the precursor. Okay, so in any kind of chamber you can do that, and there is no requirement of CVD like of chamber. In that you need to take care of a lot of things, the precursor partial pressure and all these things that you need to take care. But in this one you can this is very easy kind of tool. You can make it in any lab. So all you need is require a chamber and two kind of inlets. One is for precursor, one is for oxidant. Okay, so these should be connected with walls, and through the MFCs or so, whatever with the walls you can connect it. Just open the wall for milliseconds. These also alternately you can program these walls, which can dose your dose through which you can control the doses of these precursors, and just one outlet. Okay, and one more you required is for N2 purging. Mainly 3 lines you need required, and one is for the outlet, which is connected with the vacuum pump. Okay, this process is typically done in millibar kind of range, like 1 to 10 millibar of the pressure. So, and there are some ALDs that can be done on the atmospheric pressures as well. So that won't affect that much, but the precursor consumption is different for these. So if you want to do at lower at not at the atmospheric pressure, so a very less amount of precursor is required, because of the it won't get washed away with the purging at higher pressures. There is something that you can understand. You just need to give a thought to this one. And another thing is uniformity and conformal coverage. Uniformity is like this is the surface, and there is a growth kind of this. It is non-uniform kind of growth over this. So for and uniform growth will look like kind of this. Okay, the thickness of the deposited layer should be same for all over the substrate. And conformality is if there is a trench kind of this. Okay, so for that the growth should be like this. Okay, the material that you are growing, that should be covering the whatever steps, covering the everything, covering maybe we can say should follow the morphology of the substrate. Okay, so if there is a trench, that will be that material like Al2O3 or zinc oxide SiO2, that will be deposited over completely over the trench. Okay, it is highly conformal and uniform as well. If you can for that you just need to optimize your process with the dose time and the pulse time. That's it. Okay, this is the kind of these are the kind of holes, okay, which are 20 micron and deep, and kind of this. So Al2O3 over TiO2 is uniformly deposited over the TiO2. So this is kind of another kind of growth. So ALD, the substrate temperature also plays an important role. If the temperature is too low, that is, if we can say you are growing aluminum oxide or zinc oxide with the, let us say this is TMA or diethyl zinc, whatever you want to take. Okay, diethyl zinc is for zinc oxide and TMA is for aluminum oxide. So, but so there is the substrate temperature, lower temperature and higher temperature. Okay, so at the lower temperature, what can happen is if this diethyl zinc or TMA can get condensed over the substrate. Okay, so during the pulse time it won't get removed. The condensed, it is like a mist over the leaves or these things. Okay, that is getting condensed, that is forming a liquid over the substrate, and during the H2O line or O2 we are giving for the oxidation, the thickness will be much higher at during the oxidation. Okay, the thickness per cycle or growth per cycle will be much higher in this case, and there will be a kind of non-uniformity and non-uniformity as well. Okay, because the condensation will happen at certain points and points, so the growth per cycle will also be non-uniform in this case, and non-uniformity of the thickness as well will be there. So, and this is the one case if there is a condensation, and there are two things happening. One another thing is that there should be a reaction as well. That reaction of the of the precursor with the substrate. Okay, if it is not reacting at all with the precursor is not reacting with the substrate, so there that will be the undergrowth. Okay, because a very less amount of precursor is reacting with the substrate, and at that point there will be a non-uniform growth will happen, some kind of islands you will find in that case. So you need to increase the temperature so that it should react with the this is the kind of kinetics, so chemical kinetics. So for at a certain point after a certain a certain temperature only there will be a reaction of the precursor with the substrate. Okay, so in this and then comes a regime where the growth per cycle will be constant. Okay, will be kind of constant. So in this case this is reacted with the substrate, and it is chemi-adsorbed on the surface. So in this region there will be a very weak dependence of the growth per cycle with the temperature, and this is the our region of interest. So ALD process, this is we can call it the ALD process window. And at higher temperatures, what can happen is there can be a thermal decomposition of the precursor itself. Okay, if you are taking like in CVD, what happens is that there are some precursors like SiH4 ceiling gas. If you pass and at that temperature, at higher temperatures at the substrate, how substrate what growth of silicon happens at very high temperatures, let us say 1000 degrees Celsius. At that point this decomposes and gives silicon. Okay, this decomposes and gives silicon. That is how the in CVD silicon is grown at higher temperatures. So that can give you maybe metal deposition, this kind of growth that you can give. That thermal decomposition won't be a layer by layer kind of deposition, because most of the precursor is decomposing thermally, so there may be more than a monolayer can be there. Okay, but whatever precursor that we have designed is precursor won't react, A plus A won't react, but the decomposed precursor can go and sit down over the substrate, and that is how the growth can happen, and that will be more than a layer. So that's why the growth per cycle will be more than the whatever required, the self-limiting process, that the growth per cycle should be this much. Okay, this much, but that will be more than that. And another effect of at higher temperatures that can be seen is the if at higher temperatures the desorption of the chemi-adsorbed precursor can happen. So the substrate we have the precursor A, or the precursor is chemi-adsorbed over the substrate. At the higher temperatures this can also get desorbed. Okay, so that will give you a undergrown so the growth per cycle in this case will be lesser, because most of the precursor is already desorbed. Okay. So in typical ALD window, okay, these are the two processes that we have seen in this case. One is the condensation, another one is the reaction. So in zinc oxide case there is a at lower temperatures zinc oxide diethyl zinc DEG is not reacting at all with the substrate. Okay, at low temperatures there will growth per cycle will be very less, but if we increase the temperature there will be a self-limiting process that will come, so it will react with the substrate, and at higher temperatures there will be a desorption as well. Okay, that is why this growth per cycle is decreasing. But tantalum oxide, if you deposit tantalum oxide with this precursor, so what will happen, this will condense at lower temperatures over the substrate and will give a higher growth than expected. Okay, and after there will be a ALD window where there will be a self-limiting kind of at that point it is chemically adsorbed over the substrate, and after that it is this is thermally decomposed. Okay, at higher temperatures it will get thermally decomposed and will give you a higher growth rate. Okay, so And another thing is the effect of nucleation on the growth. So in during for nucleation, so it doesn't always follow the linear uh, growth rate. Okay, linear GPC is constant. The GPC is linear. Growth per cycle is linear at higher number of cycles. Okay, at higher number of cycles, GPC is linear. But at lower, there is a kind of more nucleation is there and under nucleation is there. So, if there is a more nucleation, so in that case, what happens is this is not only a monolayer, but it is more than a monolayer is getting deposited because of the wetting of the surface. Okay, more the wetting of the surface, more will be the growth rate at the lower number of cycles, and lesser will be the growth wetting in the sense there is a this that you can understand from if you from hydrophobic or hydrophilic kind of nature. Okay, so number of cycles but at the higher number of cycles it is this is same, because at that after some time the deposited film will be same for both the substrates. Okay, that and this depends on from substrate to substrate. If you are depositing on different substrates, this sometimes you can get this kind of profile, or sometimes this you can get this of time of that depends on the substrate to substrate, because wetting of the substrate with the precursor depends on the surface energy, and surface energy of the substrates is different. That is why you are getting a different kind of profile at the lower number of cycles. Okay, and after some layers of growth, let us say 10 or 20 layer of growth. Okay, 20 cycles. After 20 cycles, what will happen is almost there will be a full coverage of the substrate if you have done the undergrowth or overgrowth. So there will be and if you are depositing Al2O3, let us say, so the material over the substrate is Al2O3 only. Whatever it is, however it is, will like this. So, but it will be Al2O3 only. So, in that case, with the number of cycles, the growth, the thickness, increment of the thickness or growth per cycle will be constant. Will be, yes, constant. Growth per cycle is constant, and it will be linear. The thickness, increment in the thickness will be linear. Okay. And this growth rate saturates because of the deposited film underneath. Because of the same, there will be a same surface energy of the for both the substrates. Okay. And okay, let us see the effect of nucleation on the growth. These are kind of the real examples. If you are growing the Al2O3 on TiO2 substrate, okay, you have a substrate of TiO2 or TiO2 nanotubes they have given. So over the TiO2, okay, so you are giving. So during the initial cycles, this is the cycle number 11. The growth rate. This is the mass gain by the crystal monitor. It is higher during the initial number of cycles. Okay, so because of the wetting of the substrate, wetting of surface is more during that case. So the profile of that one will be kind of okay. This will be kind of the profile. Okay, initially there will be higher growth rate, and then there will be a constant. Okay, this is the kind of growth that will happening because of the more wetting of the substrate, that you can see the mass gain is higher during the initial number of cycles. But as you have deposited more, let us say after 50 cycles, the layer TiO2 layer is fully covered with the Al2O3, and then this growth rate saturates at this level. Okay, the mass gain will saturate at this level, and although both are following the same thing, that H2O adsorption and all that is following the same thing, but due to the wetting of the substrate, wetting of the a substrate only, which is TiO2, which is more due for the TMA, but TMA to TMA after Al2O3, the wetting of the substrate is less, so that is why. So it is follow, initially there is a higher growth rate during till some point, and after that the growth rate saturates, and the thickness will be linear with the number of cycles. Okay. So the another example is titanium nitride or the SiO2. So this is the TiCl for another chloride, this chloride precursor, and H2 or N2 you have given at 1000 degrees Celsius of the temperature, and for plasma at 1000 degrees Celsius. Okay, let me check. Okay, so during the initial number of cycles there is no growth at all. Well, initially nucleation is very less, so after some time, after some number of cycles, it has the titanium nitride is nucleated over the substrate, and how the growth after this point there will be a linear growth. Okay. In plasma enhanced ALD, what happens is in there previously we have discussed the thermal ALD. In thermal ALD, we are providing the energy for the reaction through the by means of the thermal, by means of heating the substrate or something. Okay, by heating the chamber. So in plasma enhanced, we can provide the energy to the substrate or to the molecules while they are reacting through the plasma as well. Okay, in the temperature required for the plasma enhanced will be lesser, because we are providing the energy for the reaction with the plasma. Okay, so it will increase the reaction rate. Okay, it will decrease the time, so lower the deposition temperatures, because we are providing the energy with the plasma, and also widens the ALD process window, because this is increasing the temperature, because with the plasma we are decreasing the temperature. At lower temperatures also there will be a reaction with the precursor with the substrate. Okay. And this is the kind of the higher growth rate. And another thing is, this is the ALD cycle, typical ALD cycle that you can see. This has widened at lower temperature only, it has widened the window for the deposition. In this one there are some disadvantages like less conformal, because for plasma should be uniform over the substrate, so it is less conformal. If the plasma is not uniform, then it won't be uniform. And as you are inducing the plasma, you are increasing one more thing in the chamber, so that will increase the cost, and less uniformity will be there. Conformal, because it cannot plasma is like a straight. Okay, it is kind of deposition, so plasma is in a straight line. So this is the kind of chamber. Over that you have a plasma something, so the plasma will be in the straight line. Okay, that it will be perpendicular. So if there are some trenches, so it won't affect on the side walls. So Al2O3 or anything at lower temperatures, if we are doing, that won't get deposited over the side walls, so it is less conform. Okay. So there are some characterizations that can be used for SEM, TEM for the morphology, conformality, and crystallinity of the roughness. So you can characterize your how after the deposition of your material or the substrate, how good your material is. Okay, so these are kind of the characterizations. In AFM you can check the morphology and surface roughness. So if whether it is following the same morphology as it was previous on substrate. Okay, XRD, the crystallinity or lattice parameters that you can see, if whether the film that you have deposited is crystalline or polycrystalline kind of the films. And through Raman you can check the film stress and lattice parameters. Film stress comes when there is a lattice mismatch, so through this you can check the how much stress is there inside the film. Okay, and XPS you can check the stoichiometry if you are depositing Al2O3, if it is uh, it is Al2O3 or ALOX. Okay, so you can check the stoichiometry through the XPS, so which is required for the good quality of the films Al2O3. Okay, and secondary ion mass spectroscopy for the doping profile, and for the contaminations you can use the SIMS. So there are various methods that have been used for SiO2 deposition. So what are the advantages and advantages of the processes that we can see? Thermal, let us say this is thermal for the native oxide growth, thermal oxidation that we have done, that happens generally at the higher temperature, so the energy input is very high in this case, and plasma enhanced CVD, the energy input is very less. Okay, but in case of for the stoichiometry, this is very less stoichiometric. It is not perfectly SiO2. Okay, but for some purposes PECVD can be useful for just for isolation kind of thing. So at lower temperatures you can use this kind of SiO2, but for the electrical purposes, for dielectric purposes, you cannot use this kind of the quality is very poor. Okay, the quality is not that good in this case, but the quality SiO2 quality at the higher temperatures is very good, because there is a reorganization of kind of thing is there, which improves the quality of the film. Okay, so these are the step coverage is poor in this case and good in this case, because this is less conformal, because plasma is kind of straight line, as we have told. There won't be any conformal coating in this case. Thermal stability is less in this case, because this is not that much stable. This is not completely SiO2 in this case. Okay, so these are things that you can see more. The dielectric constant is good in this case, which is thermal, and so that is why this thermal oxidation is used for the dielectric, that no, for MOSFET and this kind of applications. So, and another process is the physical vapor deposition. This physical vapor deposition that we can cover the next time, because I'm not feeling well today, so I'm having a bit headache. So in the next session we can cover this additive processing of physical vapor deposition. In physical vapor deposition we will cover the thermal evaporation, E-beam evaporation, and sputtering. These three things that we will cover in the next part. Okay, so thank you for attending the session today. That's it.